now so remember C32 was -2. What will be its determinant? It's going to be C32 times B32. And B32 was 1, right? So the determinant is going to be -2, just -2. So determinant of B, I will write it down here. Determinant of B, oh, you don't see it. Okay, it's going to be just -2. Very long, right? Very long, but straightforward. I mean, there's nothing new here. You just have to, every time you expand, the cofactors will contain minors of a smaller size, and then you expand in every minor, which will contain yet other minors of yet smaller size, and so on until you get to the 2 by 2, which you know how to calculate. Okay, do you have any questions? Can you hear me?
Yes دكتور بالإكزام أكيد ما حيعطونا ماتريكس طويلة.
Now, of course, you may get it. You may get a big matrix, but I hope that we will get there. You will learn how to reduce it, how to reduce it into a simpler one, for which you can easily calculate the determinant. So we haven't learned this yet. We haven't learned this yet. And I'm not sure that we will, because you see, we're running out of time already. So if we want, then of course I won't give you a 4 by 4 matrix, because this is going to give you this is going to take you about half an hour to calculate, which will be a complete waste of time. Okay, so let's finish now the homework. We still have one to go. 3.1.4. 3.1.4. Okay, they said find the following determinant by expanding along the first row and the second column. I'm going to do it one way only, either the first row or the second column. Maybe I'll do it with respect to a column, because I haven't done a column yet. So I will do it with respect to a column, okay, just to show you how it works. In fact, it works exactly the same as for a row. So I will copy it and then share it with you. So this is 3.1.4. And we are doing the determinant. So you see here, you see the bars, the vertical bars here. So this is not a matrix, it's already a determinant. So they want to directly define the determinant of the enclosed matrix, which is 1, 2, 1, 2, 1, 3, 2, 1, 1. Okay, and so let's see. Now this should be straightforward. You just pick, so we said we're going to do it with respect to the second column, okay? So start from the second column. This is the second column, so let me circle it. I'll do it in green, since it's a column. Okay. And so we start with the first entry, which is 2 times -1 to what power? To the power 2 plus 1, because it is in the, okay, let me write it correctly, 1 plus 2, because it is, sorry, it is the first row and the second column. But it doesn't matter, of course, 1 plus 2 or 2 plus 1, it's the same. But just to be clear, so you add the column number and the row number, okay? Multiplied by what minor? By the minor that you get when you remove this column and the first row. And this is 2, 3, 2, 1. Okay, plus, now we go to the next entry, which is 1 times -1 to the power 2 plus 2, because now we are in the second row and still in the second column, times what minor? Times, so I will
1
times, yeah, so removing now the second row, we'll leave 1, 1, 2, 1, right? Okay, and finally, plus 1 times -1 to the power now 3 plus 2. We are now removing the third row, right? And so what do we get? We get 1, 1, 2, 3. Yeah. So let's find the answer. Okay, 2 times -1, it's -2, right? So I'm doing the first term. 2 times, sorry, 2 times -1 to the power 1 plus 2. So it's power 3. -1 to power 3 is -1. Times 2, it's -2. And the determinant here, the minor, is 2 times 1 minus 2 times 6. So it's -4. -4 times -2 is 8. All right, so we have 8 from the first term. The second term now is 1 times negative 1 to the power 4, so it's just 1, into 1 times 1 minus 2 times 1, so it's minus 1, right? Times 1, which is minus 1. And the last term, it's 1 times negative 1 to the power 5, so it's negative 1, into 3 minus 2, which is 1. So again, another minus 1, and we get a 6. So this determinant is a 6. Okay, and now if you want to verify this, just expand it with respect to another, let's say, column, or as I said in the question, with respect to the first row, right? Yeah, the first row. I'm not going to do it, but you can do it for your homework the next time. And you should see, of course, that the answer would not change, would be the same, be the 6. Do you have any questions?
دكتور يعني لازم نرجع نعيدها، نرجع نعمل determinant تاني.
They said here in the question in 2 ways, right? With respect to the first row and the second column. I did the second. Sorry, I did the second column. So for the next time, you can do it with the first row, with respect to the first row. Okay, I think we are done with the homework, right? So let me move on now to something new. So we're done with this homework. Yes, so let me now tell you about the properties. So now we know how to calculate this determinant, which is good because they are very useful, and hopefully we'll get to the point where you can see why they are useful. But they also have properties. So I want today to discuss now with you the properties of these determinants, okay? And now I'm not going to give any proofs, but I want you to remember these properties because they are very useful when it comes to calculating determinants, when you want to calculate a determinant. So let's see, okay. Okay, so the first property of the, so here, so we are doing now this section 3.1.3. Okay, I think we have covered everything before that, right? We did everything here. Okay, so now we start now with the operations. So if you are given a matrix, right, and you want to calculate its determinant, right? Remember, not only calculate its determinant. In fact, if you are solving a system of linear equations, right? Then you can do these operations. Remember, you can switch the rows, you can multiply a row by a number or an equation by a number, and you can also add or subtract and replace some of the rows, right? And the question is, how are these operations going to affect the determinant of your matrix? Okay, so this is one thing that we need to know about. If you like, the transformation that a determinant undergoes when you change something in the rows of the matrix. Okay? So the first thing is what happens when you switch 2 rows, let's say, in a determinant. Okay, so let's say you are given a determinant like maybe I will. So I will now let me. Start a new, create a new jam, because now it's a new topic, and call it properties of determinants. Okay, so determinants. Okay, so the first operation that we can do is switching rows, right, or switching columns. It doesn't really matter, but we usually focus on rows. So what's going to happen to the determinant of a matrix if you switch 2 rows in the matrix? And let's remember how do we calculate the determinant of a matrix, okay? And I will start with a simple example of a 2 by 2 matrix. So imagine you are given a 2 by 2 matrix, let's call it A, okay? and it has this general form A, B, and C, D. Okay, and I want to calculate the determinant of A. Okay? Then to calculate the determinant of A, right? I know what to do by definition. I need simply to multiply AD and subtract from it CB. Okay. But now let's suppose that I switch the rows of this matrix. Okay. So instead of using A, I use now this matrix, which would be different, of course, a new matrix, where the rows are swapped like this. Okay. So what will be now determinant B? Okay. And by definition, you multiply the diagonal elements, which is CB, and you subtract the off-diagonal elements, which is AD. And you see that it is going to be just minus the determinant of A, the negative of the determinant of A, right? We have just, see, this determinant and this one, they are just the opposite in sign to each other, okay? So in the case of a 2 by 2 matrix, it turns out that if you switch the rows, or if you switch the columns, you can see it yourself, or you can prove it if you want, the determinant is going to change sign. That's all. Nothing more. Okay. Now, what about a 3 by 3 matrix? What about a 3 by 3 matrix? So let's take this example. A 3 by 3 matrix, it's a little bit more involved, but essentially you'll see now that the answer will come out to be the same. So again, if you switch 2 rows in a 3 by 3 matrix, the determinant is going to change sign. But now we shall see that the reason is slightly different. Okay, so let's take, for example, this matrix. How shall I call them? Let's say A, B, I would call them A1, B1, C1, okay? So this is row 1, and then A2, B2, C2, and then A3, B3, C3, right? And I will take, so I will call this matrix A, right? And this matrix where, let's say the first 2 rows have been switched, I will call it B. So now in matrix B, the difference between matrix A and matrix B is that now the second row of A comes first in B. So it's A2, B2, C2. And then I have A1, B1, C1. And then, of course, this A3, B3, C3. OK. Now, let's see. Now, how do we calculate the determinant of A, right? We can pick any row, right, and expand with respect to that row, right? So I suggest we do it with respect to row 3, right? And similarly, when we want to calculate the determinant of B, we also expand it with respect to row 3. Let's use row 3, right? And now, do you see the difference between the two? Then when you expand, remember what we do, we take an entry in the row, right? And then we calculate its cofactor, which is the minor, right, of the remaining entries. But you see, the remaining entries are going to be the entries of the first row and the second row. But they are switched in A and B. They have different positions, right? One is on the top, the other one is at the bottom. And this means that each cofactor of A will have the opposite sign of the corresponding cofactor in B, right? But since the determinant is a product of the entries by the cofactors, so what's going to be the determinant of A here? It's going to be A, if I'm doing it with respect to the last row, it's going to be A31, C31, plus A32, C32, right? Plus A33, C33, right? And the determinant of B is going to be in the same way. It's going to be now B 31, C, let me call it a different name, C prime 31, plus B32, sorry, B32 times C prime 32, plus B33 times C prime 33, okay? What I'm trying to tell you is, if you compare now these cofactors, for example, C31 and C31 prime, this one, these are opposite in sign. Why? Let me show it concretely here. So how do I get C31? C31 is, you see, it is the minor that you get from here, right? Let me do it in green. It's this minor, right? This minor here. And what is C3 prime? C31 prime, it's this one, this minor here. And you see that these two minors are the same, except that the rows are switched. Right? So this means that these cofactors will have opposite signs. And similarly for the remaining cofactors. Okay, but the entries B31 and A31 are the same. This is A31 and this is B31. They are the same. And similarly, A32 and B32 and here are the same, you see? And this means that these A's are going to be the same as these B's, but this here are going to be the opposite of these. And this means that the determinant of B will be the opposite of the determinant of A. Sorry, determinant of B is going to be the negative of the determinant of A. Do you have any questions?
No, Doctor.
Okay. And now we come to a very important thing, which you can use always when you are calculating determinants. And the thing is this. If you have a determinant which contains two identical rows or two identical columns, as for example, the one that we encountered here, not here, in the homework, which was, so I will come back to this one. Let me show you this in the homework, and then I will explain to you why you can do that. Remember, in the homework, we had a determinant which contained two identical rows. Where was it? Yeah, it was this one here. You see, the top row and the bottom row, they are identical, right? Or if you like, you can take the second column and the last column, they're identical. And what I'm trying to tell you that whenever you have a determinant which has identical rows or identical columns, two at least, right? Then you can directly equate it to zero. It's just zero. And now I'll give you the reason why it should be zero. Because of this. So let me now go back to my explanation here about the properties of determinants. I'll tell you why it should vanish. If you have a determinant with two identical rows, it must vanish. Okay, and let's take an example of a 3x3 matrix. Okay, and let's say that a 3x3 matrix has the following four. It has let's say A1, B1, C1, okay? But it happened that, let's say, the second row and the third row are the same, okay? Then my claim is the determinant must be equal to zero. Why? Because, how can I tell? Because I know that if I switch any two rows, right, it must change sign. It must change sign. In particular, if I switch the second row and the third row, it must also change sign, right? But you see that if I switch, nothing changes, right? Because, I mean, the rows are identical. If you put the last row, the second, and the second row, you make it the last, nothing changes. But on the other hand, by the property that we have seen here, it must change sign, right? So what number changes sign but stays the same? There's only one number, right? It's zero. When you change the sign of zero, it stays zero. Any other number, if you change its sign, will not stay the same, will change to another number, a different number, right? So the only number that keeps the same value when you change its sign is just the number zero, right? And that's why, so what I'm trying to tell you is that this determinant must be equal to the negative of the determinant where the second and the third row are switched, right? So ABC and ABC. But you see, when I switch the last and the second row, nothing changes. So I have a number here must be equal to its negative. What number is equal to its negative? There's only one number. If I write x is equal to minus x, there's only one solution, x equals zero. Okay? So this means that the x is equal to zero, the determinant is equal to zero. Okay? And that's why when we encountered that determinant in the solution to the homework today, I said that I already know the determinant must be equal to zero because it contained two identical rows. Okay. And do we still have time? Let me check. We still have time. Yeah, we still have a little bit of time. So I want to just mention one last property before we dismiss today. And it is this property. What if I, let's say, remember the operations are switching rows. What if you multiply one of the rows by a number? Okay, so let me show you this. Maybe one of you can come up with the answer. If you are given a determinant let me start with a simple one, a 2 by 2. So let's say A, B, C, D. Okay. And now this is, let me make it a matrix. So this is A, matrix A. Okay. And I consider now matrix B, which has the same entries, except the first row, let's say, is multiplied by a number. I'm not going to take a specific number. Let me call it K. So KA and KB. And here I have CD. Okay. So the determinant of A, I know by definition, is AD minus BC. Okay. Now my question is, how does the determinant of B compare to the determinant of A? And I can apply the rule, right? I can apply the rule. I mean, the rule says multiply the diagonal elements and subtract the product of the off-diagonal elements. So I will get KAD minus KCB, right? And you can see that K is a common factor. You can pull it out, and it will be AD minus CB, oops, minus CB, right? And this is just K times the determinant of A, because this here, AD minus CB, is the determinant of A. So you see, the determinant of B is just K times the determinant of A. So if I multiply one of the rows by any number, the determinant itself will be multiplied by the same number, will get multiplied by the same number. And this is at least for a 2 by 2 matrix. What about a 4 by 4, sorry, a 3 by 3 matrix? So let's do it for a 3 by 3, because you can prove it, okay, you don't know this, you can prove it by induction if you know how to go from one to the other. So here, we know the 2 by 2. What if I take now the 3 by 3 case? So 3 by 3 as before. Let's take, and this will be the end of today's session. So let's say we have A1, B1, and A3, B3, C3. So this is a matrix here. And the other matrix is just the same as this one, except one of the rows is multiplied by a number. Let's say the top row again. So we have KA1 instead, we have KB1 and KC1. So the same K, okay? And the rest is the same. So this is A2, B2, C2, and here A3, B3, C3. Okay? And my question is, how does determinant B compare to determinant A? Okay? Now, we know how to calculate determinant A. The determinant of A, right? What should I do? If I want to find determinant of A, I need to expand with respect to one of the rows. And if I take the top row, let's say, expand with respect to the top row, right? It's going to be what? It's going to be A11, right? Times its cofactor, which A11 is A1, times its cofactor, which is C11, plus A12, which is B1, times its cofactor, C12, plus C1, right? Times its cofactor, which is C12. Okay. What about determinant B now? So let's do it here. Determinant B. Okay, it's going to be B11, which is K times A1, right? Times its cofactor. But now, do you see that the cofactor of this is the same as the cofactor of A1? Because to get the cofactor, you need to remove the row and the column, right? And if you remove, here you get this minor, and here you get this one, right? You get the same. Right? So it's going to be C11. And similarly now, for the other one, you will get KB1 into C12. And plus here you will get K C1 into C13. And you see that all this is just K times the determinant of A. Right? So again, in the case of a 3 by 3 matrix, the determinant will be multiplied by the same number that you multiplied one of the row by.